One of the main reasons we need to use derivatives in AP Calculus is a process called optimization. Really, we're looking for the best, the most, the least of something. I'm going to run through an example. A realtor wishes to enclose 600 square meters of land and then to divide the land into two plots with a fence parallel to one of the sides. What are the dimensions of the rectangular plot that require the least amount of fencing? When you read this, the last line is a hint that we're talking about optimization. I'm supposed to use the least amount of something. That gives me a hint. I'm going to be looking for a local minimum of some equation. One thing that a lot of calculus students find hard is to create the equation. You've been looking for local maximums, local minimums given an equation. Now you have to create that equation. So let's see what that looks like. Read through this again. So we're going to make 600 square meters of land, and then we're going to divide that into two separate plots. Let's see what that looks like. Okay, well, that's 600 square meters of land. There's my rectangular plot, but I don't have the interior fence. As it turns out, it doesn't matter where this interior fence lies. If we slid this fence to the left, the length of the interior fence wouldn't change, and the perimeter of the whole area wouldn't change. So I don't really have to worry about where this thing goes. I'm going to call the length of the entire plot all the way across, ignoring the middle fence, L, and the width, or the other perpendicular dimension, W. You were given two bits of information, one about area and one about fencing. Can you tell, let's go back to our original question, can you tell whether we're going to minimize the area equation or minimize the fencing equation? Well, we're having a minimum amount of fencing, so we're going to keep the fencing equation. We're going to use that area equation for something else. The amount of fencing we need is 3 of the W lengths plus 2 of the L lengths. A W on the left, a W in the middle, and a W, this is the left. On the left, middle, and right, and an L all the way across the top and an L all the way across the bottom. Now, this isn't the type of equation that's going to be easy to find the first derivative of, set that derivative equal to 0, find where that first derivative changes signs. We want to have just L's or just W's in this equation. That's what we're going to use our area equation for. So the area equation was area is length times width, so 600 feet. So we know length times width is 600. And we could have solved for L, we could solve for W. In this case, neither makes much of a difference. All the numbers work out pretty easily. And so, super easy algebra, the length is 600 divided by the width. So now we just put 600 divided by the width in for this length. And now we have a fencing equation in terms of the width only. 3W plus 2 times 600, or 1,200, over our W. This is the thing that we're going to take the first derivative of. As soon as you write your equation, you should be looking for the domain of your equation. Now, the width of a fence has to be positive, and I suppose we shouldn't have a width of 0, otherwise we're not enclosing land. But it turns out there's no upper bound. It feels like there should be an upper bound on the width of the fence, but mathematically there's not. Let's go back. So the constraint we were given was that the area was 600. So it seems like, well, I guess the width. Can the width be 1,000,000 meters long? Sure, the length is going to be 0.00 something, but I suppose we could make that. I'm pretty sure it's not the answer though. So our domain is simply the width of the fence has to be greater than W. The width of the fence has to be greater than 0. The first derivative of f with respect to w, well, the derivative of 3w turns into 3. I'm going to ignore this 2 and this 600 like constant multipliers. The derivative of w to the negative first power is negative w to the negative second power. So now, the only place f prime can change signs is at critical values. That's where f prime is equal to 0. So we're going to set f prime equal to 0, but The only place f prime is going to be undefined is when w equals 0. That's not in the domain where we're looking. I don't want my AP reader to think I forgot about critical values or where a first derivative is undefined, so I think it's wise to make this statement. F prime is never undefined from 0 to infinity. So f prime equal to 0, pretty easy stuff. And just rearrange, you're going to move this whole 2 times 600 over w squared to the left side. Multiply both sides by w squared, divide both sides by 3, and you get w squared is 1,200 over 3. You might want to pause here and do that algebra if I'm going too quickly. So divide by 3, you have w squared is 400, so w is positive or negative 20. Well, we already said the domain we were looking for is w values greater than 0, so we'll only keep positive 20. This is not your answer. This is simply a critical value. All we saw was that f prime is equal to 0, or f had a horizontal tangent when w is 20. We need to prove we've found a place where f has a local, was it minimum or maximum? Minimum. We wanted to minimize the amount of fencing. We're going to make what's called a sign chart. So this is simply a number line. I'm going to put two numbers on here. On the left-hand side, we put in 0. On the right-hand side, we have an arrow saying, well, there's no upper bound on the domain we're looking at. The only critical value we found was 20 on the interval, so that's what we put there. I need two more details. These inputs are w's, and I'm telling the sign of f prime of w. In other problems, you might have a sign of f double prime, so it's important to label. So now, this is called a sign chart. All we care about is the sign of f prime. I'm going to put some number in between 0 and 20 into f prime and decide if f prime is positive or negative on that interval. Since f is continuous everywhere, well, I guess except for 0, the only place f prime can change signs is at a critical value when that first derivative is 0 or undefined. So let's think about this. What number do you want between 0 and 20? I'm choosing 1. So 600 divided by 1 multiplied by negative 2 is way larger than this 3, so f prime is negative from 0 to 20. If I choose a number larger than 20, I'm going to choose something easy like 100. 100 squared is 10,000. 600 over 10,000, well, that's less than 1. Multiplied by 2 is going to be less than 3. So 3 minus all that stuff is going to be positive. So I'll write a negative up here on the interval between 0 and 20 for the sign of f prime of w, positive over here. I like to draw these things underneath. This is a reminder to myself of when f prime is negative, the graph of f is decreasing. When f prime is positive, the graph of f is increasing. It also gives me a nice visual of, oh look, f has a minimum at 20. I need to explain my answer. Turns out, according to the College Board, this sign chart isn't enough. So we need to explain what we see in this sign chart. The first most important thing is f is continuous for w values greater than 0. Without continuity, f isn't going to have a maximum, a minimum, anything going on. So then I say what I see. At w equals 0, f prime changes from positive to negative. Okay, now we need the consequence of that. So f has a local minimum. Now careful, this sounds like it's done, but it's not. F prime of w changes from positive to negative at 0. So f has a local minimum when w equals, 0. Oh my gosh, huge mistake. This should be w equals 20. I must have mistyped this. At w equals 20, f prime changes from positive to negative. I don't know how I wrote 0. Oh well, I hope you'll forgive me for that. Now, if you go back, we actually weren't asked for the area. We were asked for the dimensions. We were given the area. So we need to go back and find the other dimension. We found w is 20, the thing we're looking for. So we need to find the length using w equals 20. 600 divided by 20, we get a length of 30. So don't forget to write your answer. The dimensions that minimize the amount of fencing are 20 meters in the dimension parallel to the interior fence, by 30 meters in the dimension perpendicular to the interior fence. That seems like a lot of writing. Why couldn't I just say 20 meters by 30 meters? Well, the answer would be different. Would we use a different amount of fencing if this top line was 20, this top fence line was 20, as compared to this top fence line being 30? Absolutely. And the major difference is this interior fence. So I need to mention that stuff in my answers. Let me go back. So we're going to say 20 meters is our W. That's the dimension that's parallel to the interior fence. 30 meters is the L. That's what we figured out here. That's the dimension that's perpendicular to the interior fence. There's a lot going on there. I'm sure you need a lot of practice. I hope that helped.